A very good day to Dr. Muhammad Ilyas Sobiri Muhammad Sadali. My name is Zhong from Group 3. I'll be presenting the question for Q3 A, B, and C. Let us move on to the next slide. The first question will be apply the IEEE 754 32-bit floating point standard to demonstrate how square root 2 can be written in binary format. Include the final answer in hexadecimal format. So we have to solve the square root of 2. The answer for the square root of 2 is 1.414213562. We have to solve it separately by separate the 1 and the 0.414213562. We have to find the carry and remainder for 1 and also 0.414213562. So how do we solve the separated one? In order to solve the separated one, we have to use this method, which is 1 equals to 0 times 2 plus 1, and the 1 is the carry for this separated one. So we have to solve the separated 0.414213562. 0.414213562. So as you can see from the table, we have to multiply 2 for the first column and find out whether the carry is 0 or 1. How do we going to determine? We have to determine the carry is 0 or 1 by depending on the answer after the multiplication. The first, for example, 0.414213562 times 2 is 0.8284272124. The first digit before the decimal point is 0, meaning that the carry is 0. Then the answer has to multiply by 2 again, which means 0.8284272124 times 2 will be 1.6568542248. And the first digit before the decimal point is 1, so the carry is 1. Then we have to multiply the answer again by 2 by just taking the digit behind the decimal point. We have to ignore the digit that before the decimal point, meaning that 1.6568542248. We just take the digit after the decimal point, which means we have to take the 0.6568542248 will do for the multiplication. When we have to stop the multiplication process, we have to stop it when there is a repeating answer after the multiplication of 2, or when it hits 23 times, as Mantissa maximum is 23 bits only. So the carry for the 0.414213562 is 011 01 01 00 001 00 11 11 0011. This is in 23 bits. The sign bit for this is 0, and the exponent for this is 8 bits. So 2 powered by 8 minus 1 plus power, which equals to 0, is 127. We have to change the 127 to binary. So the answer that we get is 0111 1111. The final answer for this is 0011 1111 1011 0101 0000 0100 1000 and we change the binary to hexadecimal. You'll get 0 times 3f v5 04f3. That is the answer for Q3A. So we'll proceed with Q3B. So for the Q3B, the question will be describe the binary coded decimal code and how addition in BCD are performed. So what is BCD? BCD is named as binary coded decimal, which the number system which has the binary numbers to represent a decimal number. BCD is a kind of decimal number which contains 10 digits which start from 0 to 9, and the binary will be 0000 to 1001. If the decimal digit is single, then the BCD will be in 4 bit. But if the decimal digit is double, it will end up to be 8 bits in total for the BCD. The conversion from decimal numbers to binary and binary coded decimal are shown in the table for the next slide. So as you can see from the table, when the decimal number is single digit, the binary number and BCD number will be having the same output, and it is in 4 bits. But when the decimal number is double digit, which means decimal number are 10 and above, the BCD number will be no longer in 4 bits. It will become 8 bits, which the first 4 bits indicates the first number of the double digit decimal, and behind 8 bits is indicating the second number of the double digit decimal. Let's move on to the next slide. I will be explaining further on the BCD addition. For the BCD addition, there is 3 cases. First case will be when the output of sum is less or equal to 9, the output is correct. No further action needed on this. But for the second cases, the output of sum is less than 9, but final carry is 1, the output is incorrect, and we need to add another 0110 binary number, which the decimal is 6, only to get the answer correct. We will look through the example to have a better image on how the BCD addition works. So for the last case, case 3, when sum is larger than 9, the output is incorrect by comparing it with decimal when we're doing conversion. So we have to add another 0110 decimal of 6 to get the output correct. So we will be doing the example. For the first example, first case, output of sum is less or equal to 9, final carry is 0. The answer is correct, so no further action is needed. So based on the example, 0010 decimal number of 2 add with 0110 decimal number of 6, the output of sum is 1000, and convert it to decimal, it is 8, so the output is correct. No further action has to be done for this. So let us move on to the next example. Case 2. Case 2, output of the sum is less than 9 and final carry is 1. 1000 decimal number of 8 add with 1001 decimal number of 9. The sum of output is less than 9 and the final carry is 1. So we have to add 0110 decimal number of 6 to get the correct output. So 0001 plus 0110, we get 0001 which the first 4 bit is 1 and behind 4 bit is 7. The answer is correct. So for the last example, case 3, when the output sum is larger than 9, final carry is 0. 0111 plus 0010 the answer is 01117 and 1101 decimal number of 13. The answer is incorrect due to the last 4 bit is larger than 9. So the last 4 bit we have to add with another 0110 decimal of 6 to get the answer correct. 1101 plus 0110, the answer is 10011. The first digit of 1 is carry. So just now the first front 4 bit is 0111. We need to add the carry in the answer. So we need to add the carry in the answer is 1000 after adding the carry. Then the last 4 bits will be 0011. Final answer is 1000 0011. The decimal number of 83. The answer is correct. This is how the BCD addition works. So we will now proceed with to the next slide for the Q3C. For Q3C, the question is describe the gray code sequence and its advantage over the normal binary numbering sequence. So what is gray code? Gray code is known as reflected binary coded, which invented by Frank Gray. The gray code is an encoding of numbers so that the adjacent numbers have a single digit differing by 1. This gray code, we can say it is well arranged, not weighted, and every transition from one to another are only involving 1 bit change. So based on this table, we can see that there is a slightly difference between gray code and binary number. In the previous slide, I was mentioning one important point, which is the 1 bit change when switching. So for example, based on the table, the decimal part and decimal 6, there is 2 bit change, which is 1 to 0 and 0 to 1. Then the other 2 bits remaining the same. But in gray code, for decimal 5 and 6, we can see that there is only 1 bit change, which is second digit 1 to 0. So what is the advantage over the normal binary number sequence? The advantage is the 1 bit change when switching. Due to this 1 bit change, it reduces the switching process and the reliability of switching is improved. That's why gray code are widely used to facilitate error correction in digital communication. For example, some cable TV system. Not just that, gray code provide a lower power consumption, which really benefits a lot in digital communication. That's all from me for this 3 questions. Thank you so much.